Hi, grade 11 and 12. Welcome back once again. We are still continuing with Euclidean geometry, grade 11 to 12 transition, and this is the revision series. And this is our session 3, where we'll be focusing on theorem number 3. Without any further ado, let's get straight to it. Okay, theorem number 3. It states that the angle subtended at the circle, at the circumference of the circle actually, by the diameter is a right angle, right? Very, very simple. So we said that that angle is in a semicircle, right? Because what we have is that you have your diameter AB here. So your diameter will subtend an angle that will be what? That will be a right angle at the circumference, only at the circumference, right? We don't want you to come and tell us that this is a right angle here, because it's totally incorrect. It's not at the circumference, right? So this theorem says, in a nutshell, according to the given circle sketch below, if AB is a diameter, and we can see AB is a diameter because it passes through the center, joining its endpoints on both the circumference, right? So then it will subtend an angle at the circumference, which will be what? Which will be a right angle. In other words, angle C will be equals to what? Will be equals to 90 degrees, right? So that's what the theorem states, and we're just going to prove this theorem. Very, very simple proof. You don't need to struggle, right? If you watch the previous session, it was session 2, theorem number 2, you'll be able to understand this proof really, right? So as we proved, we are given the diameter AOB. As you can see, we are required to prove that indeed angle C is 90 degrees, right? How can we prove that? Okay, so we can start by saying angle AOB, right? Angle AOB, this angle here, is equals to what? 180 degrees. And why is AOB 180 degrees? Because angles, some angles of what? Of a straight line. We know that some angles of straight line are supplementary, that is, they add up to 180 degrees, right? We know another theorem. Okay, we have a chord here. Can you see this chord AB is subtending this angle at the center, right? We talked about theorem number 2 in the previous session, and we said that angle subtended by the chord at the center of the circle is equal to 2 times angle subtended by the same chord but at the what? At the circumference. Okay, so it means that we can now deduce that angle AOB, which is 180 degrees, must be equal to 2 times angle C, because it's an angle the circumference there, right? Okay, so we can replace AOB, and we have to give a reason. Angle at center is equal to 2 times angle at what? At circumference. Okay, and we talked about that theorem in the previous session. So very simple, just go and replace AOB by 180 degrees to angle C. To solve for angle C, we divide both sides by 2, then angle C will be equals to 180 degrees divided by 2, which is equals to what? 90 degrees, proving that angle subtended by the diameter at the circumference is a right angle. Okay, let's quickly take a look at the converse of this theorem. Okay, so the converse theorem 3 states that if an angle subtended by the chord at a point on the circle is 90 degrees, then that chord is a diameter. That is, that chord will pass through the center of the circle, right? So it's actually the opposite, or rather the reverse, not the opposite, the reverse of the actual theorem 3. That states that if you have a diameter, then it will subtend a right angle on the circumference, right? Now it's taking that in a reverse way to say, now if you just have a chord, right, without knowing that that chord is a diameter or something, you just have a line now, right, and it's subtending a right angle on the circumference, then that line will be called what? Will be called a diameter. That is, it passes through the center of the circle, right? Okay, as you can clearly see here on this illustration, they just had 90 degrees here, right? And they have a line here, AB, which is subtending this 90 degrees at the circumference. Then we can deduce that, oh, our AB is actually our what? Our diameter, right? And that is the converse theorem 3, right? That's the converse. Okay. Okay, let's now quickly look at an example, right? Okay, so the question said, solve for x, given reason or reasons for your answer. Okay, how can we solve for x now? We can see that our x is inside a triangle, but we have a problem. The problem that we have is that we don't know this angle here, right? We just know we are given 60 degrees and x, but we don't know that angle. But from the theorem, we know that AOB is a diameter and it subtends a certain angle at the circumference. And what's that angle? It's 90 degrees. Okay, so we're going to start by telling them that angle C is equals to 90 degrees. And our reason for that is that it's an angle in what? In semicircle. Angle in semicircle. Or someone can give a reason to say angle subtended by diameter, right? Angle subtended by diameter. But mostly they want you to give this reason angle in semicircle. But we can see it's just an angle subtended by diameter. We know that it's a right angle. In other words, it's 90 degrees. Okay. So yeah, that's gonna be the case. Now it's quite easier to solve for x because we have this angle which is 90 degrees, we have 60 degrees, we have x, right? Remember the geometric basics that we started with in session 1? We can solve for x by what? The idea of angles in a triangle, right? We know that angle C plus angle A plus angle B will be equal to what? 180 degrees, right? Because we know some angles of what? Of a triangle. Some angles of a triangle, they all add up to 180 degrees. In other words, they are supplementary. So we can replace that one with 90 degrees and our A with x and our B with 60 degrees. And simply go and solve for x, right? 90 plus 60 is going to give us 150. Then x will be 180 minus 150, which is going to give us what? 30 degrees. So x is equals to 30 degrees. And that's how we actually solve for it using this theorem. Okay. All right, let's also look at this quite interesting example. They are saying solve for all unknown variables given reasons for your answer. Okay, so we have to solve for x, we have to solve for y, we have to solve for a, right? Given reasons for what? For our answers. Okay, how can we solve for these things? Okay, someone can say I want to start solve for y, right? Because we've just done a theorem here, right? You are told that O is the center of the circle, right? And they want you to solve for all these variables. All right. So to solve for this, we know if O is the center of the circle, then DOB is a what? Is a diameter. What do we know about a diameter? The angle subtended by the diameter at the circumference is a right angle. Also this side, the angle subtended by the diameter at the circumference will be what? Will be a right angle. In other words, it will be 90 degrees. Okay, so you can fill up that information and we can quickly go and solve for what? For y, if we just use that information. So I'll first write for them angle C is equals to 90 degrees, angle in what? In semicircle, angle in semicircle, right? We know that the angle in semicircle, that is an angle subtended by diameter the circumference, which is 90 degrees, right? Then to solve for y, I'm just going to say angle y from this triangle, angle y plus 22 degrees plus 90 degrees is equals to what? 180 degrees, because we know these are some angles of a what? Of a triangles, and we know that they are supplementary, right? So to solve for y, we're just going to say 180 minus 90 minus 22 degrees, which will give us 68 degrees. So our y is 68 degrees. So it's quite very simple to do that. All right, so we got our y is 68 degrees. Let's go and solve for x now. Right, okay, how can we solve for x? Look at this. You must now be thinking of the key basics that we started with when we introduced this theorem, right? So that's one of the things that makes Euclidean geometry quite not easy for most of you guys, because it has to do with relational understanding. You have to be relating prior knowledge, you have to be relating the basics, you have to be relating those other theorems, thinking them at one time, right? At once when you are solving a problem. But the more you practice, the more you become perfect in a way, the more you are able to think of them in a problem, right? So the idea is simply just practicing and practicing so that you can be able to recall what's needed in the question. All right, so for us to solve for x, look at this, quite interesting. You have your radius, right? We talked about the radius in section 1 and we said all radius are what? Are equal, right? And if all radius are equal, then what triangle are we forming there? A or B? What's that triangle? Is it what? It's an isosceles triangle. And what do we know about the isosceles triangle? That base angles are the same, right? It means that this angle will be the same as this one, meaning that our A2 is going to be equals to what? It's going to be equals to x, right? By which reason? Angles opposite equal what? Equal sides. Or someone can say base angle of an isosceles triangle. Angles opposite equal sides. And what are those equal sides that we are talking about? Is because AO is equals to what? I mean OA is equals to OB, right? And those are our radius, right? So we have x there. So we can simply solve for x because we have a triangle that is filled up, right? So it's going to be what? X plus 60 degrees is equals to what? Is equals to 180 degrees. Because what? Some angles of a triangle. Some angles of a triangle are supplementary. So to solve for x, it's going to be very simple. 180 minus 60 is 120 degrees divided by 2. Divided by 2, then our x is equals to what? Is equals to 60 degrees. All right, so x is equals to 60 degrees. Okay, so we can just go and replace x with 60 degrees, and this is 60 degrees. They can give you a follow-up question to say the triangles now change. What kind of triangle is this? Is a what? Is an equilateral triangle, because all sides are equal now, because all angles are the same. So you can see you have to be relating with the basics that we started with in session 1. All right, okay, let's now lastly go and solve for A, right? Look at A here. How can we solve for A? How can we solve for A? A is an angle at the center, can you see? But subtended by what? By arc, sorry about this, let me use a different color. Subtended by this arc AD, right? It's subtending an angle at the center, which is A. Then the same arc AD, it's also subtending an angle at the circumference. Can you see? Here is it, X. What do we know? Angle at the center is 2 times angle at the what? At the circumference. Now you must be thinking of theorem 2 that we did in the previous session, right? So our A will be equal to 2 times x, right? Because angle at center is what? Is 2 times angle at what? At circumference. Angle at center is 2 times angle at the circumference. Then we can solve for A will be 2 times 60, which is what? Which is equals to 120 degrees. All right, so our A will be equals to 120 degrees. Or someone might actually solve it quite simple to say, oh, some angle of a straight line are what? Are 180 degrees. Then that one is the fastest way, right? But I just wanted to show you that we can use more than 3 theorems in one question. So using a relational understanding approach to say don't actually think of a problem independently, but of one theorem, but connect the theorem. Think of them at once in one question if the condition are met. All right. Okay, this marks the end of our lesson. Thank you very much for watching. Thank you very much for joining us today. This was session number 3, Theorem 3, Revision, grade 11 to 12, Transition. Otherwise, that's all for me. Coming up next is Theorem number 4. All right, we'll meet there. And goodbye.